Okay, hello CS11, welcome to lecture 8. For lecture 8, we'll cover more comprehensions and something called index-based comprehensions. So, quick review ng cover natin so far. So last lecture we covered the range type and we've seen backtracking in action. So one of the things that recursion can do. We've also seen asserts, docstrings, and you've seen the ternary operator from the lab lecture. Okay, so let's go back to comprehensions. In comprehensions, you can destructure bind as well. So here's an example. Points is a tuple containing pairs of integers, and you can access the two integers in each pair through this comprehension syntax. So prods contains the products of the tuple pairs, the integers in the pairs for each pair from points. So the syntax goes as follows. We're building a tuple. We're getting x times y for each x and y in points. Okay, so the structuring bind here happens here, x, y in points. Okay, so instead of a direct equal sign, we are going through all the points in points, each pair, and then assigning the variables x and y to each pair of values or integers. You could also do something like this. There is a built-in function called enumerate. What enumerate does is it tacks on the index of each element as we go through a sequence of elements. So you can get the index of each one and the element itself. So creates a pair. The first element is the index, and the second element would be the element from the sequence itself. So in this case, our element is a pair, and we are using the structuring bind to get the two values at the same time using variables. Let's demo enumerate quickly. Okay, enumerate. For example, we have a sequence 1, 2, 3, or let's make it strings. Res equals tuple pair for pair in enumerate sequence. Res now contains the following elements. So it goes through all of the elements. For each element, it pairs it up with its index in the sequence. Okay? So yun yung enumerate. This is a built-in function for the next lab. It may be disallowed, but in the future you can use this. Alright, what else can we do with comprehensions? Quick review. Remember that we can chain comprehensions. Ito yung implementation ng Cartesian product using comprehension. So compared to the recursive implementation, it's quite brief. So returning a frozen set where we are pairing each xy for each x in the sequence S and for each y in the sequence T. Quick check, is there a difference between the following two? So the order of the chain comprehension is swapped for these two examples. So before you verify on your own terminal, you can pause the video and take a guess if these two frozen sets are the same. Okay, did you pause? What did you get? So if you run this, you will see that these two are the same. Let's do that. Where's our terminal? Let's have S be equal to 1, 2, 3, T be equal to A, B, C. Okay. Let's do this for the first part. Then for the second frozen set, let's swap the order of the comprehensions. Okay, we show F1, F1. This is F1, F2, this is F2. So for frozen sets, these two are the same. But if you will notice, there is a difference here if order matters. So if for X in S appears first, it will determine X first, so it will take an element from the sequence S first and then pair it up with elements of T next. So first it will pick 1 and then it will pair it up with A, B, and C. Then it will pick 2, then pair it up with A, B, and C for the first chain comprehension. For the second one, Y gets determined first, so for each Y in T, so the string A gets chosen first and then it will be paired up with for each X in S. So 1A happens first and then 2A and then 3A. In the previous comprehension, 1A happens first and then 1B and then 1C. So it's a different ordering. If we did not use frozen sets, if this was a tuple, should get the following. So 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C. But if 4Y in T goes first, the ordering will change. So 1A, 2A, 3A, 1B, 2B, 3B, 1C, 2C, 3C. So for tuples, ordering matters. For frozen sets, ordering does not matter. And you can verify that these two tuples are not the same because ordering matters in tuples. Here are more exercises to check your understanding of chained comprehensions. So here we have a new comprehension. You can pause the video to try to guess which, or try to think in your head which of these tuples are equal to this comprehension. Okay, did you pause? If you will verify, it is equal to the second one. And we have more examples. You can try figuring this out on your own. You can pause the video before running this in the terminal. In general, you may notice a pattern, how to remember which ordering happens when you specify a comprehension, one way to remember the ordering would be, you can think of it as moving from general to specific. Here's an example of that. If you are going through two sequences, you can think of the first sequence as getting a major version or a more general numbering, and then for succeeding sequences in the chain comprehension, you can think of it as being more specific in the numbering. So you can continue this. This is an example with just two chain comprehensions, but you can keep going with 3 or 4 or even more sequences. Okay, number 2, don't memorize the ordering pattern, just run the code in Python to verify. Okay, number 3, we'll be going back to this in a future lesson. Okay. Aside from chain comprehensions, we could have comprehensions where subsequent comprehensions depend on variables defined in earlier comprehension. So here we have a function called getAllLetters, returning a frozen set containing all ch. For each word in words is a sequence of strings. So for each word in words, we are getting each ch in word. Ch stands for character here. So this comprehension on the right uses the word variable that was declared earlier here. Okay, so if you try to run this, you will see that it gets all unique letters from all the words in this sequence of words. What if we swap the ordering of the comprehensions here? You can verify this. So, okay, let's try running this. Let's write this function, get all letters. Let's get a bunch of words: apple, banana, carrot, okay, so we have all the unique letters from all the words. If we try to change the ordering of the comprehension here, so it's a name error because in this Python evaluates the comprehensions from left to right or from as you write down the chain comprehension. So for ch in word fails because word is not defined anywhere before you encounter this comprehension. So only the correct ordering works this time because of you need to, when you use a variable name, it has to be defined earlier before you encounter it. Okay. Here's another example. You can go through this on your own. Try to practice figuring out what happens with chain comprehensions that where variables depend on previous variables. This one uses range. Remember how range works. It goes from the starting number 2 up until this number -1. Okay. So try to simulate this in your head. If you are not sure, you can always run it in the Python shell. Alright, so let's try to use ranges in combination with comprehensions. So what are ranges good for? Apparently, ranges go well with indexing. So recall that indexing starts at 0. We start counting at index 0 for sequences, and then the last index for a given sequence is its length minus 1. Range also works similarly. If you give it a value n, integer greater than or equal to 0, range will provide you with the integers starting at 0 and until n minus 1. So we can say that ranges are great at producing indices for sequences, and we'll be using that in our comprehension. So the difference between what we've done so far is we're going through each element in the sequence in order, like this, for our previous encounters with comprehensions. However, in cases where we want to control the order in which we access elements of a sequence, we may be able to use ranges to gain more control, aside from going through all of the elements just in sequence. So we can generalize by using indices this time. Here's an example. So the enumerate built-in function, we can actually write something that is almost the same as what it does. Here's a function enumerate from 0. We return a tuple containing pairs, where each pair contains I and the ith element of a given sequence, where I is I gets all the valid indices in the sequence for a given sequence, and we can get that by using this comprehension for I in range, the length of the sequence. So this goes from 0 to length of the sequence minus 1, and we are accessing each element of the sequence using its index paired up with its index. So this is what enumerate does. Let's test this code. Okay. Use enumerate from 0 here. Okay, it works. Similarly, you can also do this as an exercise. You can write enumerate from, where the starting count does not necessarily start at 0, it starts at some arbitrary integer input integer d. So it's quite easy to write. You can quickly write this down. You just need to modify this function width, and once you've written that, enumerate from 0 follows from this generalization. Just pass the value 0. Okay. So what else can we do with indices? So if you want to have access to elements outside of just going through the elements in the order they are given in a sequence, we can use indices. So both recursion and comprehension can use indices. Here's an example of recursion using indices. Here is our reverse function from before. So this one goes through all the elements by using slices. Well, it gets the first element and then recursively goes through the rest of the elements. But we are doing slicing here, this part. You can avoid slicing, or another way to do this would be using indices instead of slicing the sequences. Here we write a new function underscore reverse with two inputs, the sequence and I, which is an integer. The interpretation of this function is we are getting the reversal of the sequence from the ith element onwards. And here's the recursive definition. If I is greater than or equal to the length of the sequence, then there are no more elements to reverse, therefore we return the empty tuple or sequence. Otherwise, we get the reverse. We get all the elements of the reverse of the sequence starting at I plus 1 index, splat that, then add the ith element at the end of this tuple that we are building. So it does the same thing, except we are using manipulating indices in this one. And to solve our original problem, we start at index 0. So all elements, the reversal of the sequence from index 0 onwards, which is the whole sequence. You can do this also. You can implement reverse using comprehension and indexing. Hint would be you can use ranges and you can count in reverse using ranges. Okay? Or you could do arithmetic as well using your normal range. So pick one method that you would like. These are just exercises. In practice, if you want to reverse a sequence, just use the idiom that we learned from Lablec 0, which is the reverse slicing here. Okay. Here are more uses of indexing in comprehensions. All suffixes. A suffix is a slice of the sequence that includes the last element of the sequence. So what varies among suffixes would be the starting element, and all starting elements can be enumerated using all possible indices. So for each I in the range, the length of the sequence, so that's 0 from 0 to the length of the sequence minus 1, we are getting the slice from I onwards. Okay? Or maybe this is the implementation of all suffixes. We add a +1 to the range. So both of these can work, just depends on your definition of suffixes. If you are concerned with non-empty suffixes, then the first implementation is the one that does it. If you consider empty sequences as a suffix, you can include the second implementation is the one that is correct. Okay, so this works for strings as well. Okay, so depending on the problem that you're trying to solve, pick the one that has the correct definition. Alright, we can also do all pairs using the indexing that we did. So how can we think of all pairs of a sequence in terms of indices? If you think about it, every pair can be written as a tuple containing two elements, sequence I and sequence J, where I and J are indices, and I should not be equal to J to avoid pairing an element with itself. And since I and J are indices, they are at least 0 and they are less than the length of the sequence. And they are not equal. Hence, we have this inequality expression. But how do we implement this in code? We have the following. Well, we define all pairs to be a tuple containing pairs sequence I, sequence J for ij in index pairs, given the length of the sequence. So what's left to do would be define this index pairs function. We want to generate all unique pairs of indices ij. How can we do this? We can use chained comprehensions like this. First, we fix our I, go through all possible I. Given the value for I, we will go through all j greater than I. And we should be able to go through all the pairings. So here's what it looks like. Index pairs n. So n would be the number of the length of the sequence. Return tuple containing ij for I in range n. Then for each I, to ensure that j is not equal to I, and to ensure that no pairs get repeated, j starts counting from I plus 1. Okay? Let's try to run this code. Okay. Turn tuple ij for I in range n, for j in range I plus 1 n. Okay. Okay, so this is index pairs. Let's try printing all pairs from this tuple. Okay, so that's how it works. Okay, so that's index pairs. You can also implement index pairs like this with a different ordering for the comprehension. Try to figure out what the difference between the two are. Alright, let's try all substrings again. This time we'll include empty substrings. How will we solve this using indexing and comprehensions? So, key thing to note would be that a substring is just a slice of a string. Specifically, if We have index I and index j. The substring can be denoted as S slice from I to j. So that includes characters from I until j minus 1. So you can try to convince yourself that all substrings can be written that way. So now, all we need to do to generate all substrings would be to generate all possible pairs of ij. This time, I can be equal to j, in which case we get an empty substring or an empty string. And also this time, I and j can be equal to the length of s. So we are getting substrings from the end of the string, which are empty. Well, this could include the last character of the string. So if I is the length of, no, if I is the length of s, then you should get an empty substring. Okay, so similarly, you can define all substrings like this as slices for all ij in index pairs 0. Index pairs 0 includes empty slices, and we can define index pairs 0 like this. So I now runs in the range 0 to n, or 0 range n plus 1, so that's from 0 to n. J can be equal to I, so we can start counting at I until n plus 1. Okay, so this inequality is generated by this chain comprehension. Or you could change the ordering as well. Okay, try to run both and see the difference between the two. So here we tried to do the code step by step, but if you get used to writing comprehensions, you can just write down the whole thing in one go. So this includes the pairs that need to be constructed as well as the comprehensions for the indices. All right. If you're unsure with your answer, just run your code and see if you get the correct output. And to test your code further, we recommend you add assertions. So if this is the input, put the correct output here and then equate them. If your code runs without any errors, then your code works, assuming your test cases are exhaustive. Okay. One more example. Given a sequence, an inversion is a pair of elements x and y such that x appears to the left of y but x is greater than y. So another way to think about this is, if you have a sequence of numbers, for example, you are looking for pairs x and y such that they are not in order when you sort them. So here are some examples. Or in terms of indices, choose a pair of indices ij such that I is less than j, but the element at index I is greater than the element at index j. So we can write a function that finds all inversions by using the second definition. You can use indices. Here's the implementation of all inversions. So how did we come up with this? We are doing a filtering technique. We are trying all possible pairs of indices. So this is similar to the pattern that we saw before, this one. But we add a filter to it. We are only choosing the index pairs where the element at index I is greater than the element at index j for all the pairs where j is greater than I. And we should get the following result for this input. Okay, so this pattern here, going through all the pairs of indices, you will use this a lot. You can extend the idea for triplets or quadruplets or whatever. Just stack on more variables and make the next variable dependent on the previous one. So you can extend this. These are two comprehensions chained together. You can extend this to 3, 4, and so on. And here's an example of that. Given a sequence S of non-negative integers and a number m, find all triplets of elements of S whose sum is at most m. All triplets of elements of S, so we need all possible triplets. Elements may be picked multiple times, so in terms of indices, that means indices that can be equal to each other. So I'm guessing you can visualize the code by now. So it looks like this. Well, we actually don't need indices here, since there's no restriction that elements need to be unique or elements at different positions need to be chosen. So you can just go through all the triples. But we need a condition where the sum of the triples, members of the triple, is at most m, less than or equal to m. So at most means less than or equal to m. And we're returning those triples. How do you get the triples? You just do it like this. Return tuple ABC for each A and S, for each B and S, for each C and S. Note that this allows A to be equal to B or B to be equal to C, or all of them to be equal. Here's a more direct one. Instead of using two functions, you can just write the whole thing down in one go. Let's try this. Triples with some bound. Okay, let me write this in code, in the editor. Some bound. Turn tuple ABC for A and S, B and S, for C and S, A plus B plus C is less than or equal to M. Need an example. sorry. Triples with some bound, and let's give a sum. I don't know, 10. The answer should be, let's see. That's a lot. But you can verify that all of the sums here add up to at most 10. Okay, that's a lot of triples because how many elements are here? 1, 2, 3, 4, 5, 6, 7. That's 7. There are 7 cube possibilities here. Possible triples. There are only a few. How many triples were there? Let's print out the line. Okay, 178 out of 7 cube. What is 7 cube? 343. So there are a lot of results. Okay. Here's a slight optimization. What do we mean by that? If you will notice, once you choose a value for A, the sum, you can now restrict the values you can choose for B and C, because the sum, target sum, is now M minus A, right? So we can add these conditions to stop the search much faster. If, for example, we're going through each B and S, if you can check if A plus B is less than or equal to M, then we can eliminate possibilities. Okay, so here it only performs the check at the very end, but we can check much earlier as we go through. As we pick one element at a time for the triple, we can check if the triple that we are building is still valid, for such that the sum is still less than or equal to M. So if we pick, okay, so we pick all A if A is less than or equal to M, otherwise we go over M. Then we pick B such that A plus B is less than or equal to M, and so on. This is the final check. This does optimize things, but there's a catch. There's an assumption that we are making here. So again, this notice the syntax. This if is tied to this comprehension here. This if is tied to this comprehension here, and so on. So the syntax still holds. Okay, what assumption does this code assume? It assumes that S does not have negative elements. If S has negative elements, then these optimizations actually make our function wrong, or the output wrong. So try to figure out why this assumption is necessary for this code to work. Okay, next, what else can we do? Given a grid, its transpose is obtained by flipping it along the down right diagonal. So here's a grid or a matrix, if you've already encountered those. We are transposing it by flipping it along the down right diagonal. Down right. So where is that diagonal? over here, the diagonal here. Or in other words, if you take each column of the grid and make it a row, you should get the transpose of the grid. So 1478 here, make it the first row. Second column is 2587, make it the second row. Third column is 3696, make it the third row. How do we do this? You can try to break down the problem step by step. Let's try to do it using comprehension. Okay, so let's try some wishful thinking. You can still use wishful thinking even outside of recursion. So here's our function. We want to transpose a matrix. We need the dimensions of the matrix. You're essentially returning a tuple containing each column of the matrix for so if we know how many columns there are, we can assume we have a function called column that takes the jth column of that matrix. Then we go through each column starting from column 0 until column c minus 1, where c is the number of columns in the matrix. Okay. First, we need to define dimensions and column. Dimensions is easy. You can verify this from our grids lecture. Number of rows would be the length of the matrix. Number of columns would be the length of any of the rows of the matrix. So, simplify things, we use row 0 to compute the number of columns. Then return R and C as a tuple. You can write assertions to test that your code works. The dimensions function. Column, remember what column the function signature is. Given a matrix and a column J. And we can do this using comprehensions. To get a column from a grid, to get the jth column from a grid, notice that you are going through all the rows for a given column J. So you can use indexing. You need, so all the rows, that's row index 0 to r minus 1, and access all the elements in those rows, and J is fixed, so that's it. So here's column. You need the dimensions of the matrix again. Well, you only need R this time. And you return a tuple containing the elements at row I and column J for all I in the range R. So that's row 0 until row R minus 1. And J is fixed from the input. And that's how you get a column. And that's it. That's the whole transpose function. Okay. Here's another problem. We've encountered this before, but this time we'll use comprehension to solve it. All palindromic substrings. We have all substrings written as a comprehension. Just need to filter. So we just add in an if to the comprehension. And is palindrome. This palindrome function is written like this. So moving forward, when you are solving problems, get into the habit of decomposing the problems into step by step into its components. So here, first we did the all substrings part, and then next we did the palindromic part. And finally, we wrote down the function for checking if a string is a palindrome. Okay, now that we have both recursion and comprehensions, we can actually combine them together to make more interesting functions. Here's an exercise. The hint would be you will need, or it's much easier to do this with both recursion and comprehensions. Or I think you actually need both. So we want to enumerate all length k subsequences of an n tuple. These are also known as combinations. What do we mean? Subsequences are part of a sequence where you remove some elements. For example, this is a sequence. If you remove some elements such as 1 and 2 here, you get 2, 3, 1. So that's a subsequence. Note that the order of the relative order of the elements should still be correct. So for example, here are the length 2 subsequences of this tuple. Or in other words, these are the size 2 combinations from this sequence of numbers. Get it like this. Okay? How would you solve this? You can use both recursion and comprehensions. Hint, try some wishful thinking. You can solve combinations of size k if you have the answers for combinations of size k minus 1. You can start by choosing the first, when you're building a certain combination, you can start by choosing the first element to put in the combination. And there are a lot of choices. So you can pause the video, try it on your own, and then let's see the solution afterwards. Okay, did you pause? What did you get? Let's try solving it. Okay, combinations of sequence and k. So what's the wishful thinking here? Well, what are our choices for? So what do we need? What do you want to return? We want to return a tuple containing all the combinations. So let's try returning a tuple. Okay. So you want to choose. So here's the idea. Let's assume that we can solve something like this. Okay. And then wait, what do we need to do? How did we generate these combinations? So for all combinations, it has a starting element. So for example, this, if we choose this as the starting element and we have k equals 2, then for this element, we only have these elements that are left that we can pair with this element if we chose this as the first one. So the combinations that come from choosing this as the first element would be, here they are, 2, 1, 2, 3, 2, 2, and 2, 1, right? 2, and then all of these, okay? This is for k equals 2. For k greater, the idea remains the same. If we choose this to be the starting element, we can pair, or we can combine. We can insert this first element into the combinations using these elements, but k is now k minus 1 because we already chose one element. Okay, we are building length k subsequences, so if we already chose one element, then for recursively we can get the combinations for the other elements, but k is now one less. So that's how we'll do that. First, what are our choices for the first element of the subsequence? Well, we have all the elements as choices, except we need to stop somewhere. For example, if k is equal to 2, we can only choose these 4 as the starting elements. Because if we choose this as the first element, then we no longer have anything to partner it with to build our combination. So in general, for some given k, I think we can choose from 0 until, in terms of indices, the elements that we can choose for the first element in each combination would be up until the length of the sequence minus k. But in terms of indices, we need to add 1 to that in order to include this one, for example. For example, this is the length of this is 5. 5 minus k, 5 minus 2 is 3. So range until 3. But we want to include 3, so we have a range until 4. So that would be the length of the sequence minus k plus 1. Hopefully that makes sense. So we want to build. Let's choose this first element of each combination. And assuming we have all the combinations from, okay, let me write this down for now. We are choosing all possible starting elements, which you can represent using an index from this range. The length of the sequence minus k plus 1. For all possible starting elements, we will pair it up with all combinations that we can get from a recursive call. This is the wishful thinking part. If we chose the element at index I to be the first element, we can only now choose the element starting from index I plus 1 for the rest of the combinations. Then this is now k minus 1. Okay, this is quite complicated, but I hope you see the wishful thinking here. This assumes that we have all the combinations from this smaller version of the problem, starting at index I plus 1 of the sequence, and we need to form k minus 1 length combinations. But we're not done. This is recursive, so we need a base case. Our base case would be if k is equal to 0. That means we don't need to get anything. There is only one, so we need to return a tuple, right? But this tuple should contain all combinations of size k. There's only one combination of size k, which is the empty combination. This is crucial. Okay. Let's try this. Combinations. Let's try the sample input from the slides. Okay, this might look hard to come up with, but try to go through the visual thinking and understand what's happening. Actually, don't need to do this. The range works in such a way that you cannot find combinations for starting elements that are way too far to the right for a certain value of k. But let's put it anyway to better represent what's really happening. We should get the following output. And we got it. 2, 1, 2, 3, 2, 2. 2, 1, 1, 3, 1, 2. 1, 1, 3, 2, 3, 1. 2, 1. Okay. It works. Alright, that's combinations. Now, assuming combinations is available, can you solve the following problem? Enumerate all subsequences of an n tuple. So all subsequences, not just the length k subsequences. So we can reuse our combinations code to get all subsequences of different lengths from 0 to n. So subsequences, we use our combinations function and we generate all subsequences for all lengths k in range. So that's from 0 to n inclusive, so that's why we have length sequence plus 1 here. So for all the lengths, and then for each subsequence in all the subsequences of length k. Okay. Here's an exercise that you can do on your own, although we'll be uploading code for this. You can pause the video and try to do this on your own. Permutations this time. This time, enumerate all possible reorderings of an n tuple. Actually, let's do it right now. These are called permutations. All the possible reorderings of an n tuple. There are n factorial of them. For the tuple 1, 2, 3, here are all the reorderings of the tuple 1, 2, 3. There are 6 of them. Okay, output in any order. Alright, you can pause the video before proceeding, but we also will be using recursion and comprehensions in combination here. Alright, did you pause? How would you solve this? Again, wishful thinking, try to solve the problem step by step. For any permutation, you can always choose the first element, right? This is the first element here, here, and here. And then we can pair up that first element with all the permutations of the elements that were not chosen. And that's the idea. I'm going to return a tuple containing for a given element e, and then we're going to get the rest of the, for all possible For all permutations of the rest of the elements that are not E, put them here and then put E here. So this generates all permutations, right? For E in the sequence, we run into some trouble. I have to make sure that I'm able to get the sequence, the elements that are not E. So maybe I can do something like this. I'll use indices instead. Then use this to go through all the elements of the sequence. So here I'm choosing the first element to put in building permutations. Okay. So for the initial choice, I have the choices are all the elements of the sequence. So I'll go through the whole range of indices from 0 to the length of the sequence minus 1. And then for each permutation of the rest of the elements of the sequence, which would be, how do we express that? We should not include index I since we already chose the element at index I to be the first element of the permutation. So sequence would now be something like this. Let's exclude index I and then include start at index I plus 1. So sequence before index I and the sequence after index I. Okay. So this is recursive again. We need the base case. Base case here is actually similar to the base case in the combinations. If we have an empty sequence, there's only one permutation of the empty sequence, which is the empty permutation. We are returning a tuple of all the permutations, so this is the correct answer for this one. So tuple containing the only permutation of the empty sequence is the empty sequence. You can verify that 1 factorial is equal to 1. So we only have one permutation for the empty sequence. Sorry, that's 0 factorial, I should say. Let's try that. Let's print the permutations of 1, 2, 3. Or better if, let's try using strings. And we have this ABC, ACB, BAC, BCA, CAB, CBA. Okay. So hopefully you can understand these functions. We are now combining recursion and comprehension. The recursion part, because we are using wishful thinking to solve the whole problem. And the comprehensions part for when we need indices. Go through a bunch of indices in some range. Okay. Let's wrap this lecture up. Given a string S and an integer k squared. One last problem. Find all of its substrings of length k. String S and an integer k. All of its substrings of length k. So substrings of length k look like this. We have a starting index and then the next k minus 1 elements. Here are the inequalities. The starting index should be a valid index. And I plus k should be less than or equal to n. Here's an attempt. right? We're getting all substrings like this. So S is a string here. For I in range len S plus 1. The question is this correct? Let me write the code down. Substrings sk return tuple I plus k for I in range len S plus 1. Let's try all length k substrings of not sure, apple maybe, then length 3 substrings. We should get app, ppl, and ple, right? Is this correct? Oops, this is wrong. Why? We forgot to exclude. So our range here kept going even if we no longer have enough characters for the substring. So we need to bound, we need to stop our range at this point when we just have enough letters to create a k-length substring. So how do we do that? By the way, well, we detected it by running it. If you added an assertion as well, showing the expected output for a given string, then we can also catch that our code is not working. How do we fix it? Well, we will use our inequalities. So note that I is between 0 and n inclusive. I plus k is less than or equal to n. So if we transpose k here, I is less than or equal to n minus k. So n is the length of the string. So we replace n here by n minus k. So we have len s minus k plus 1. Let's try to fix that now. Minus k plus 1. And we should get the correct answer this time. Okay. As a bonus, we get an alternative all substrings implementation using our all length k substrings function by going through all possible lengths of the substrings. And that ends lecture 8. Here are the readings for the next lecture and for some advanced study. That's it for lecture 8. More comprehensions and index-based comprehensions, and we've seen recursion and comprehensions being used at the same time as well. See you in the next one.